All right, folks, so let's work on simple harmonic motion. It is a new unit, and we're going to talk about some brand new stuff. So what is simple harmonic motion kind of simply defined as? It's any motion that has a back and forth, I would say, motion to it. So for example, like a swinging pendulum, but there's also a second component necessary in order to truly make it a harmonic motion. So one, you need that back and forth motion, but also you need the force we're going to call the restoring force, or what brings it back to equilibrium, to be proportional to for how far away is from that equilibrium. What does that even mean? So let's look at the picture here we got for this pendulum. We have the center line, we'll call that center line equilibrium. If we look at the pendulum motion, of course it's going to go back and forth, pretty easy to say there. However, what about the restoring force? Is that proportional? Well, the restoring force when the pendulum's towards the bottom is pretty small. It's the force or the component of weight or force due to gravity pulling it towards the center. Not going to be very much. However, when it's almost perpendicular to the ground, that restoring force is a whole lot more. So what we see is that there is a proportionality. The further you are away from equilibrium, the more force needed. Okay, that's kind of it. So let's look at pendulums specifically. We're going to kind of unpack with these notes. These notes shouldn't really take too long. We're just kind of starting to understand what simple harmonic motion is, and that's a back and forth motion that has a proportional force from equilibrium. Okay, when we look at a pendulum, there's going to be a couple of variables that we're just only going to observe at. We're not going to do kind of the trig-based math on the restoring force or the component of the force or free body diagrams by any means, but we are going to look at how long does it take for a pendulum to swing back and forth. And that is denoted by this period right here, T. So the period of a pendulum is how long it takes to do one full back and forth motion. L represents the length of the string, and then G is gravity. So you got length and then gravity. So when it comes to a pendulum, there are essentially two variables that affect how long it takes a pendulum to swing back and forth. Sorry, my eyes really itchy. Okay. The first variable we're going to look at is the length of a pendulum. Well, the length of the string, man. Oh. The length of the string, which is recorded in meters, makes sense. The longer string you have, the longer it's going to take that pendulum to swing back and forth. However, it's not really quite a linear relationship, so you notice it's under a square root sign. We'll get there in a second. The other thing that also affects it is gravity. So gravity is, on Earth, it's 9.8, what we talked about in class. Sometimes we'll even use 9.81 meters per second squared. I'm pretty sure we're going to only use 9.8 on when it comes to the homework. I didn't double check that before starting this video, so kind of maybe ask me after if you're curious which one we use for the notes or the homework. I'm pretty sure we're going to use 9.8, but I needed to double check that before we got started. And period, since it's a unit of time, it is going to be recorded in seconds. How long does it take to do one full back and forth? Okay, look, that's it. Looking good. Now, notice I'm going to kind of attach a link to this video here down in the description where it's looking at pendulums with varying lengths, and you can kind of hit up with this little mathematical chaos where pendulums have a kind of a rhythm to them. I think it's really cool. What you notice is that all the pendulums look to see if they're out of sync, but after a while they all come back in sync again. And that has to do with like greatest common factors, and when pendulums are swinging, there's going to be at some point where they all swing together again at the same time. Okay, let's do two example problems and kind of be done for pendulums right now, or at least unpack them as far as what we need for the notes. Okay, Visitor visits a lighthouse, determine the height of the tower. She ties a spool of thread, makes a simple pendulum. She hangs it down around the center of the spiral staircase to the tower. The period of oscillation is 9.4. What is the height of the tower? So this tells me my period is 9.4 seconds. It's how long it takes to go full back and forth. And since we are on Earth, we're going to use gravity is 9.8 meters per second squared. From here, we're just going to use the period of a pendulum formula. Notice on the poster kind of provided on the wall, it says T sub P because we're going to look at springs later on, but right now we're only looking at pendulums. So pendulum is 2 pi square root L over G. Yep. Okay, all this is kind of just plug and chug from there. The rest is just algebra, so let's do that. So we have 9.4 equals 2 pi square root L over, we know it. We're looking for L over G, which is 9.8. So let's do some simple math. So I'm going to do 9.4 divided by 2 pi equals square root of L over 9.8. Quick maths. What's that? 9.4 divided by 6.28. And that gets us at, we'll round that out to 1.5. So let's come on over here. And let's just say that's 1.5 equals L over 9.8. Well, we got the square root of that. How do you get rid of a square root? Well, you square both sides. So let's do that. If we square both sides, the squares cancel out that square root. And so I'm left with 1.5 squared equals L over 9.8. So 1.5 squared is 2.25 equals L over 9.8. Multiply both sides by 9.8. You get the length or the height of this tower to be 22.05 meters. So the height of this tower is 22.05 meters. Cool. That's kind of it. Let's do one more example problem and we'll kind of call it done. A block of unknown mass is attached to a spring. Oh, nope. You know what? It looks like we're only doing one because this is a spring problem. So here's what we got so far. We should have already done something a little bit in class, looking at what variables actually affect the variables of a pendulum. And one common thing that a lot of people get stuck on is mass. Mass actually doesn't affect the period of a pendulum at all. Because if we were to look at the free body diagram, mass actually cancels out. So let's look at what variables do affect the period of a pendulum, and that's only length and gravity. All the other ones kind of are a moot point or so negligible we really don't look at them. Okay? All right, man. That's going to be it. If you have any questions, let me know. It's going to be plug and chug and just kind of a simple, small lesson before we get into springs kind of later in a couple days. Okay. Good luck. If you have any questions, let me know.